guess we wait for a few minutes to allow some people to join.
Okay, okay.
Yeah.
I think I'll also message some of the attendees just because we started late, so that they'll come in.
Mm-hmm. Yeah. Okay, so Assalamu alaikum wa rahmatullahi wa barakatuh. Today I have the pleasure of introducing Dr. Mohsin Elahi for our research cafe. He serves as the operations lead and senior quantum scientist at the Center of Excellence, Chinal Quantum AI, which is a Srinagar-based deep tech company in India, where he oversees strategic, high-impact initiatives at the interface of artificial intelligence and quantum computing. His work spans advanced research domains including quantum machine learning and quantum reservoir computing, ensuring that AI technological direction remains aligned with global industry trends and emerging scientific breakthroughs. In his leadership role, Dr. Ilahi manages, uh, mentors a multidisciplinary research team guiding the development of innovative, scalable solutions that push the frontier of both AI and quantum technologies. He also plays an active role in advancing international collaboration, cultivating research partnerships with leading institutions, both academic and industrial worldwide, to leverage global expertise and drive impactful scientific and technological outcomes. So, without further ado, let's hear from Dr. Mohsen Yahi on quantum machine learning and its potential applications. So, the floor is yours, Mohsen.
Jazakallah, Saad Saab, for this kind introduction. I hope my screen is visible and I'm audible. Can you just acknowledge it before I go ahead?
Yes, yes, we can hear and see your slides well.
Okay, thank you. So, first of all, a brief about myself. I have gotten inspiration to go into science from Aligarh Muslim University because I can see there in the Maulana Azhar Library at Aligarh Muslim University, which is third largest university library in Asia, where one of the replica of the Nobel Medal of Professor Abdus Salam is there. He donated it after visiting shortly after winning the Nobel Prize in 1979, and I have documented this whole inspiration in one of the articles which was motivated by the one of the biographers of Professor Abdul Salam, Mr. Muhammad Zakaria Work. He lives in Canada, basically from Karachi. So he insisted me to write about it, and I have documented it. It has been a huge, inspiration. One Nobel Medal replica is in ICTP. One is at Aligarh Muslim University, and one is at the home, perhaps with his son, Mr. Ahmed Salam. So this is one of the great motivations. And then just after finishing my PhD around 2019, there was this historic address by Khalifatul Masih at UNESCO on 8th of October 2019, and this further pushed me a lot to work in the more aggressively in the scientific domain. And this was followed by the, I would say, this was the immediate trigger when this Amra UK conference, it was the 10th international conference, and it was very much publicized because earlier Amra UK efforts were not that much published on MTA, but because Huzur was gracing the occasion and it was of international character, and the pain in this address gave me a lot of pain, and I thought about why should not we start something like Amra in India as well. And by the grace of Allah and the prayers of Khalifatul Masih and the support from the Nazara Talim India, we initiated the Amra India chapter, and we got the first conference done on March 4th 5 2020 at the historic Masjid Aqsa in Qadian Darul Aman. And this is, since then it has been a great journey because we got connected with Amra UK. Many of the members are also part of Amra UK, and we feel like we are coming together and fulfilling the vision and mission which Khilafat Ahmadiyya has, you know, which the kind of expectations they have from us. But I just want to mention here, because this is very much connected with my personal journey. When first conference happened in India, Khalifatul Masih gave us a message, and in that message he quoted that the quote from Muslim Maud Raziallahu anhu. At one occasion he has said that while sitting in a train or a plane, I have a feeling in my heart that I wish they were built by Ahmadis and that they were the owners of these companies. So this was in a way for me a motivation to go from academia to industry, because there I can build something. Of course we can build something in academia as well, but I think there are more, I would say, the more emphasis is in industry to build the things. I shifted towards industry, and the transition happened in 5th of August 2022 when I published my first paper on archive, and it was more of industry grade paper, because I worked closely with an IBM quantum scientist, Dr. Uksanul Haq. He is the CEO currently and chief scientist at the company in which I work. And along with my cousin, he's an MD brother, he was also being mentored, and we got this paper published. And this gave me a huge confidence that I can go into this domain of quantum computing, one of the emerging frontier, or kind of the technology which was out there at that time, very much in the domain of science and tech. So this is a brief about my journey from going from academia to industry. Today I'm going to talk about why we need these quantum computers in the first place, and then I will talk about why we need to use this quantum computing in AI domain as well, and this will bring me naturally to the quantum machine learning and one of its potential applications at quantum reservoir computing. So first things first, to begin with, I believe there may be some um, members who may not have much idea about quantum. I would like to give a brief intro about quantum. So this quantum comes from this paradigm in physics which was discovered in the beginning of the last century, called quantum mechanics, which is a kind of physics which helps us to understand what is happening at the microscopic level inside the atoms, and what happens with the kind of dynamics of molecules and all that. So this is a kind of paradigm which physicists have developed over the last century, and it's one of the greatest achievements of all science and technology which happened in the last century. In the beginning it started, but the kind of behavior at this microscopic level is very weird and strange. And recently people have I would say it has been now 50 years, people started thinking about, can we use this weird behavior of these microscopic objects to build something to compute. And the answer is yes. Quantum computing can be considered as the application of quantum mechanics, and it can solve some of the problems which our classical computers, the normal computers which we have on our tables, cannot solve. And two of the hard problems which we have, which the scientific community is facing, is that simulation of these molecules. Let's say if we have a drug molecule which has many atoms, and to simulate its behavior, the current classical methods are not enough. So we need to have something different, and this is the initial motivation which Richard Feynman, in one of the conferences in 1982, this is how the history goes, he proposed this idea: we better have some natural quantum mechanical device to simulate this quantum matter, because fundamentally all matter is quantum. To simulate that, to model that, we need to have some other device, not this 1010 device, the binary kind of quantum computer we have. Of course it has its own power, but when it comes to simulating these natural materials, the matter at the fundamental level, it struggles. Second, hard problem is like, we have these encryption schemes through which we protect our data in the cybersecurity domain. We have one of the way our WhatsApp works. They claim that they have this encryption one to one. Nobody can hack it, but of course it is still prone to hacking, because after all the algorithm is based on some mathematical problem, and the famous one, the RSA algorithm, which is based on the factorization of prime numbers. It's very difficult for the classical computers to factorize a big prime number into its two factors, because as you know, the prime number has two factors, and these classical computers are not, it's a hard problem for classical computers. But for quantum computers, it's very easy, and it has been proven mathematically by Peter Shor that we can break it. That's why the lot of emphasis on these days is on post quantum cryptography, and you will see a lot of news coming out, because this is a potential hard problem is for classical computer, but it becomes very easy, and hence it becomes very important to develop, to design algorithms which can help us to protect our data. And that's what Khalifatul Misi also mentions, we should come into this domain of cybersecurity and develop. So this is one of the reasons. Another reason is like, as you know, the history of quantum, this classical computer, it started when it was first of all very big. There were vacuum tubes, then the transistor revolution came in the 1950s, then we got these ICs, the transistors came to the level of a, these atoms, and then you hit a wall, because at the when you start making transistors of the size of atom, the quantum effects come into picture, the quantum tunneling phenomena, like that, they don't let it go down. So it naturally brought us to the another paradigm, which is not just an extension but a completely new way of looking at computation. So this is a brief history what I was talking about so far. It's not just it started yesterday, it has a long history. It came out as a fruit from quantum mechanics, which started in the beginning of the last century, and this is a kind of timeline, the major milestones which have happened in the domain of quantum computing. Now that every one is racing towards this new kind of computer and different, it's not just it will be built out of transistors and these silicon chips. For quantum computer, you have different kind of hardware. So some people are building quantum computers based on this nuclear magnetic resonance devices, some are building it based on rapid ions, some based on Myron and topological. IBM is taking, sorry, Microsoft is taking a lead in this, and then we have Diamond, this NV, nitrogen vacancy centers, and one of our MIT professors from Germany is also working in this domain, not using it for building quantum computer, but using it for biological problems like diagnostics and other things, because they can do the precision diagnosis. And then the superconducting ones are the major platforms used for building quantum computers. Then there are photonics based, then there are neutral atom based, and many more. So this shows the kind of diversity and the kind of new paradigm which has opened up in front of us to do the computation for the hard problems. If we see the current state, like the classical computer was initially of the size of a big room. If you say quantum computers today, they are also very big. You see these wires, this golden type of wires, but there is a huge refrigerator also, because you have to protect the quantum systems from the external environment, because they are very fragile, very delicate, and they get disturbed by small effects coming from the environment. And why people are investing a lot in quantum computing? Because it has a promise, because it can be used in many application domains, ranging from chemistry, drug discovery, to AI, machine learning, finance, cryptography, and so many other domains. Even to do a fundamental physics, people are trying to do a black hole physics kind of simulation on a quantum computer. It's a huge application. I have just named a few here, but my focus will be here more on machine learning. How can we use it in AI? But before I go there, I would like to mention briefly, maybe there are young guys here, they would like to know how what it takes to become a quantum computer specialist, or jump into quantum computing domain. It's an interdisciplinary field. You need bit of mathematics, you need physics, you need exposure to computer science. I have got a bit of all of these three domains, but currently I'm trying to slowly try to understand the hardware part as well, because recently we have tied up with a hardware quantum computing company which is based in India, Qubit Force. It's called Qubit Force, and the CEO was yesterday here. I mean, say in a conference in Srinagar recently, and we discussed it a lot. They are building the cheapest quantum computers, 5 crore worth Indian rupees, and they are selling it, and they have been quite successful. So that way, if I would. Come to the basic fundamentals of quantum computing, one should know the way we have in classical computer these bits, classical bits, zeros and ones, and but in quantum computing the basic unit of information is qubit, called qubit. And it's interesting if you go down to the history of this qubit, and it's really inspiring. You know, this qubit word comes from this measurement which we earlier used to do. If we have this length from elbow to the tip of the finger, let's say this finger. So it is very much mentioned in Bible, and the who coined this term, the quantum information scientists, they draw the inspiration from that, and rather than calling it qubit, qubit, they called it qubit. It's a, you know, bit of quantum information. So it's this bit of quantum information is not like 0 or 1, like, you know, just two states. It is a mixture of both of them. It can be 0 and 1 simultaneously. It's like a dial, as I shown on the slide. Am I moving my slides? I could see that. uh, can anybody acknowledge? Are my slides moving?
Sorry, yes, the slides are moving. Mohsin Sab, we can see the slides.
Okay, thank you. I just wanted to confirm because. Okay, so let me go back. One thing is that the basic unit of information is a qubit called. It can be unlike the classical computer, which is 0 or 1. It can be in the mix. It can be a mix of both, and then there are other quantum phenomena which are being used to power quantum computing. Is one is called entanglement. Superposition is more like having both 0 and 1. The famous Schrodinger's cat, it can be dead or alive before you open the box. If we have the radioactive device inside, and which can hammer the poison bottle, and you don't know before the, because the radioactive phenomena is random, before opening the box you may not know what is happening inside the box, whether the cat is alive or dead. This kind of a superposition, no, having both the states simultaneously. Entanglement is one more phenomena which recently got the Nobel Prize, and I will talk each one of them briefly. And then we have quantum interference, because, you know, at the fundamental level, this electron or these quantum objects behave like waves, and when we have waves, they can interfere like the water waves. So these are the three main ingredients or three main properties which are using by quantum computers, which gives the quantum computers the kind of power they have in solving some of the hard problems. Going back to this superposition, as I told, that qubit is kind of an information, quantum information, which can live in the mixed state, 0 and 1 together, the way it's explained usually by the Schrodinger's cat example. It can be both live and death. And if we talk about in the form of a meme, it could be this Schrodinger's phone. It has fallen down, and before you see the mobile phone, whether the screen is broken or not, it's in the both states. It's like that kind of a phenomena, and it happens at the microscopic level. We have another entanglement which was very in the beginning, in the 1930s, when this entanglement idea was born. The great scientists like Einstein did not believe in it. He used to say it's a spooky action at a distance. But now that entanglement had got a Nobel Prize, entanglement is being used to power quantum computers. It is being used as a resource kind of a to do the computation and solve some of the hard problems. And then we have the quantum interference, which is used to make algorithms efficient. And these are the kind of three main major phenomena that are being used to develop quantum algorithms and solve some of the hard problems. So it's like, if I summarize, it's like these three quantum phenomena, which we don't usually see in the form at the classical level. They are being the pieces, like piece of a jigsaw puzzle, they are being put together to build algorithms. So for it has been more about why quantum computer, and what is the kind of phenomena, or what is the kind of resources, quantum resources which power it. Now coming to the algorithms part, people started, once the idea of quantum computing was conceived, people
Saad Saab, I think Mohsin Saab's internet might have gone down. He just left, I think.
Yeah. He I messaged him through WhatsApp. He says he's reconnecting.
Perfect. We'll just wait. Apologies, everyone.
Yeah, apologies.